Have you ever asked yourself how your operating system enforces process isolation and memory protection? In today's video, we are going to talk about virtual memory. By the end of this video, you'll understand the fundamental idea behind it and what the entire security is based on. Let's dive in. First of all, virtual memory is just an abstraction of physical memory. Every time you launch an application or program on disk, a process gets created in memory. More details on how processes are created will be covered in another video. Don't forget to subscribe. But let's get back to our today's topic. A memory area reserved for a new process gets logically divided and organized in regions. Regions that are called virtual memory areas on Linux systems. They are used for different purposes, such as for code, data, heap, stack, or other memory mappings. Some areas are static, and some can grow and shrink at runtime depending on your program's needs. The actual program code or image is located in a code segment, marked as executable and read-only. Global and static variables or constants you have defined in your code are stored in a data segment. All memory chunks you have requested during a dynamic memory allocation are located here. In case your program is dynamically linked, all required shared objects are mapped here. Even command line arguments and environment variables passed to your program are mapped here to make them accessible. Everything that is not mapped cannot be accessed. This whole virtual memory address range is called virtual address space. Each process has its own virtual address space assigned by an operating system, and a process never gets to see any physical addresses. It can be considered as a free playground for each process. Any access beyond these limits is a policy violation and leads to a process termination. Now that we already know what a virtual address space is, let's see how it is implemented on a Linux system. In general, a process control block is a data structure used by an operating system to manage process information in memory. On a Linux system, such a data structure is called task_struct. Each time a process is created, a new task_struct gets created as well. It is a very large and complex data structure which contains a process memory management descriptor, which in turn contains further data structures and pointers, as you can see here. Multiple pointers are being used to define those virtual memory areas we have seen before. And one of these many pointers is used to point to a top-level page table. Page tables are fundamental building blocks when talking about virtual memory. They are very crucial for security and must be protected from being compromised. Attackers often modify page tables via memory management bugs to escalate their privileges. We will come back to page tables later and also cover more details in future videos. But first, let's take a look at an interface that is exposed to user land via proc file system by Linux. It can be used to examine processes' virtual memory map and layout. Here we can see exactly where all virtual memory areas are mapped to and whether they are readable, writable, executable, private, or shared. We already know that physical addresses never become visible to running processes. But how are those virtual addresses finally get translated into physical addresses? The short answer is via page tables. Every virtual memory access is intercepted by the CPU and gets translated into a physical address by the memory management unit using those prepared page tables as an input. Once address translation is done, the CPU internal memory controller takes over control and does the rest. Page tables are special data structures populated by the operating system and stored somewhere in memory before a process is marked as ready to run. They can be considered as large mapping tables that map a virtual page number to a physical frame number. A page table entry also contains some flags to indicate whether a page is present in memory or swapped to disk. In addition, some other security attributes are included, which we will tackle in one of our next videos. A process is not able to modify physical memory owned by another process as long as it is not explicitly shared, because there is no virtual address in its page tables that maps to physical memory of another process. Two processes can also have exactly the same virtual address space, but with completely different mappings. That's how process isolation and memory protection work on a higher level. An isolated and protected execution environment is simply created by memory mappings. Let's quickly summarize what we have learned so far. Our running process never gets to see any physical memory address. A physical memory address that is exposed to a user LAN process is considered as a security risk and can be used to bypass exploit mitigation techniques. In order to access physical memory, every virtual address accessed by a process gets translated into a physical address. The address translation and memory isolation is based on page table information. Page tables are per process. They define a strict memory access policy. Page tables are populated by an operating system and are stored in main memory. Page tables are used by memory management units for policy enforcement. Page tables must be protected from being compromised to ensure strong isolation. That's all for now. Thank you for watching and see you in our next video.